Hey dudes. Well, the topic here is solubility. This is a continuation from looking at percent yield the last time you were looking at something. So solubility is such an important topic. Okay, and you will see, we will not just talk about if something is soluble or not, we're also going to talk about how much they're soluble. Now, that will be a little bit later. And looking at if soluble, what is the concentration of the solution? Eventually, we'll do a whole bunch of mathematical work, preparing different solutions, how diluting the solution can actually change the concentration, and stuff like that. You'll love it because this topic is actually very real and very useful. Hey, at the same time, this actually sets you up for topic 9 later on and topic 8. Okay, and it's actually super useful when we talk about topic 7 as well. So this little topic right here, okay, in topic 1, sets you up for a lot of future topics that we will be looking at pretty much in the near future. For some of you in the far, or actually near, well, whatever, it doesn't matter. So, hey, let's talk about solubility, okay? And let's talk about how things are dissolved in water and how reactions are being brought about. Now, looking at this reaction right here, where I took silver nitrate and reacted with sodium chloride. Now, we've done this type of things before. We understand the fact that this is a double displacement reaction. And by looking at something called a solubility table that I was introduced to a few weeks ago, I know this reaction exists because if I were to switch the partners up, Ag, okay, will now be with chlorine to give you silver chloride. By looking at the solubility table, I know that silver chloride is a precipitate. And this is how we indicate a precipitate in a chemical equation, given, of course, the state S, which stands for solids. All right, so that is a precipitate, which is great. Okay, and what else? Well, you're also going to get sodium. Notice I'm using the color to let you guys know exactly how the displacement is being brought about. Okay, so I have here sodium nitrate. And this is going to be aqueous. Now, you are able to write that equation for me if I were to give you the reactant and you were to tell me the product exactly the way it is right now. The good thing about this is that you don't need to balance it, which makes it, ratio friendly in my point of view. 1 to 1 to 1 to 1. Okay? Now, let's take a look at what exactly is going on here. If you were to do this as an experiment, if you were to actually perform this chemical reaction, what are the steps that are being taken? So let's take a look at the reactants, okay, to begin with. Let's take a look at silver nitrate. To prepare a silver nitrate solution, obviously you need water. Okay, you need water. Because water, in this case, will separate the silver and the nitrate into their ions. Now, how do I know that silver nitrate dissolves in water? Well, it's pretty simple, actually. All you have to do is look at the solubility table, and it will tell you that, silver nitrate, that's certainly dissolvable. In fact, all nitrates are dissolvable, so that's an easy one to know, right? Now, this is what you're going to do, okay? You're going to take the silver nitrate crystal, Okay, it comes in a form of crystal, and you're gonna drop it in water so it dissolves. So therefore, it matches with this aqueous state, because that's what aqueous means. Meaning that silver nitrate is not in its crystal form, but is in its dissolved form in water. So you're gonna drop this in water. And what happens when you drop it in water? Well, it separates and becomes ions, just like what we saw with acid. So silver will be silver plus, nitrate will be NO3 minus. Now, obviously, silver nitrate is an ionic. I can really say ionic. Nitrate itself is covalent, but then silver nitrate is put together through electrostatic interaction, and water have the ability to break that interaction into its ion component. Okay, so in this beaker right here, there's probably lots of Ag plus, and there's probably lots of NO3 minus. Okay, so that's what we call aqueous, and that's exactly what happens when you drop AgNO3 in water. They break apart and become ions. Now, in this situation, as long as water is capable of dissolving AgNO3, this solution right here is said to be unsaturated. Okay? Meaning that if you were to keep dropping AgO3 in here, and it keeps making Ag plus and NO3 minus, this is still unsaturated. Now, there will be a point where you drop this in here, and it actually doesn't separate. It kept itself as AgNO3, and you can see that. You can see that. Why? Because the crystal that you dropped in here did not dissolve. It stayed as a crystal. What's happening here? Okay, it stayed as a crystal. No matter how much you shake it or how much you swirl it, it stays as a crystal. It just doesn't dissolve. We say at this point, this solution is saturated. All right? Every chemical dissolvable in water or not, most likely you're talking about dissolvable in water, has what we call a saturation point. Or later on, you will learn solubility constant, KSP. Okay? AgNO3 has a certain KSP, NaCl has a certain KSP. This constant tells you at what point will the amount of water you have will not be able to dissolve any more of the salt. Okay? Like what we see right here. If we drop silver nitrate in our beaker of already saturated solution of AgNO3, and you'll notice that AgNO3 doesn't dissolve, you know that you have reached saturation point. Okay? Now, there are of course ways to dissolve this actually. If you were to heat this up, okay, make this a little hotter, they will eventually separate. Okay, we call that supersaturation. But that's not something we want to look at today. Okay, so make sure you know the difference between unsaturated and saturated. So it was unsaturated, like right here. Okay, this was unsaturated because your solution are able to dissolve more AgNO3. But once it doesn't dissolve anymore, we call this saturation. Hopefully, this is something that you understand. All right, so in an experiment, that's exactly what you did. You took AgNO3, you dissolved in water. By dissolving in water, you are seeing a solution, okay, where you don't see the AgNO3 crystal anymore, but what's really inside your solution is a whole bunch of Ag plus and NO3 minus. So you should not see more than one phase. Same with NaCl. Okay, same with NaCl. You want NaCl to react with AgNO3? Well, very simple. Drop NaCl crystal in water. Drop your salt in water. Okay? Because when NaCl sees water, but the polarity of water actually will pull apart Na and Cl, just like how it pulled apart Ag and NO3. So what's really inside the solution? Well, a whole bunch of Na plus and a whole bunch of Cl minus. Let's draw two. Why not? Okay? Make it consistent. All right. So we've done it. We've dissolved AgNO3 and we dissolve NaCl. So what we really mean by dissolve is having water in its polar ends to pull apart the cation and the anion. So this is my next step. My next step is that I'm going to take a bigger beaker. Let's use a different color. Okay, we're going to take a bigger beaker right here. Okay, and I am going to dump this in here. And I'm going to dump this in here. So in other words, I'm going to mix the two. This is what's going to happen. Okay, right now you have a whole bunch of Ag plus. You have a whole bunch of NO3 minus. They're dissolved. And then, of course, you have your Na plus and your Cl minus. Okay? Now, this is the amazing part that I like to show. We know for a fact that by doing the chemical equation, you make AgCl, silver chloride, and that is a precipitate. What we meant by precipitate is that AgCl are insoluble in water. They don't dissolve in water. So when Ag finds Cl, they will get together and they say, hey, let's hook up. We are a precipitate. We will form a solid. That's exactly what's going to happen in here in this beaker. Ag will make its way to bond with Cl. Oh, let's do it like this. Okay, you say, hey, Cl, let's get together. We're supposed to be together. We're supposed to be together being this AgCl that we are. There's two of them, actually. Okay? So these guys, actually, let me erase them. Okay? Ag and Cl will get together happily ever after because it is a solid. It is way more dense. They will actually sink to the bottom to give you this precipitate that you're asking for, I guess. Okay. Now, you'll notice that the other product for this reaction is NaNO3. Okay. Does NaNO3 get together like we see with AgCl? Well, of course not. It's stated right here that they stay as an aqueous state. They actually don't really bond together, but they are, of course, floating around in this solution as Na plus and NO3 minus. You can't even call them spectators, which we will see later on. But, of course, because NaNO3, okay, sodium nitrate, is soluble, so being in a solution still full of water, they're going to stay separated. Okay, they're really just ions that hangs around in this solution. But what you can see, of course, is the solid that was being formed here. So this is the detail behind this reaction. This is actually exactly what happens. Okay, and you can easily detect that with your eyes, but sometimes you might just have to let it settle for a few minutes before you actually see the precipitate. Hopefully this is something that you guys are I guess happy with. Okay. There are some examples that I have for you. Okay, and this is nothing more than showing you graphically exactly what happened in a double displacement reaction. Okay, so because of that, we're gonna write this a little differently. Okay, we're gonna write this a little differently. We're gonna write what I call Ionic Equation in the basis of what happens to AgNO3 and what happens to NaCl. Okay, so let's do this. This is called total ionic equation. Okay, that's what it's called, total ionic equation. In a total ionic equation, you are writing this equation right here. Okay, based on what happens inside water. So you see how we did this graphically? So we're gonna do it in a chemical equation type of aspect. So let's take a look at how we are gonna do this. Let's look carefully. Okay, so this is the base double displacement reaction that we all know how to do. So what we're going to do with the total ionic equation is that we're going to break all the aqueous apart into their component ions. So instead of saying AgNO3, I'm going to say Ag plus NO3 minus, because that's exactly what happened in aqueous situation. Okay, this one is easy because there's no coefficient. Well, there's coefficient, but the coefficient is 1. And I'll show you in another example what happened when the coefficient is not 1. Okay? Plus, okay, we did the same thing with NaCl. NaCl is soluble, so therefore NaCl will break apart to give you Na plus and Cl minus. Okay? Exactly what happens in my beautiful picture. Now, what happened here? What happened after you mix the two together? Well, we saw if a precipitate were to form, they have the ability to find each other. Okay? And that would be AgCl. So let's write that down. AgCl. They are not going to break apart because they won't break apart. They're not going to form ions. Okay. Plus, well, NaNO3 will though. So you have, oh, I'm running out of space. Na plus, okay, and NO3 minus. That will also be in aqueous state. Okay, that is a total ionic equation. Okay. Really just illustrating exactly what's happening, inside a solution. All right. Now, that's not what I want though. In a chemical equation, okay, here's some rules here. In a chemical equation like this one, or any chemical equation that you will learn later on in chapter 9, that if there is an identical chemical on the left and right side of the equation, they can be canceled. Let me show you what I mean by that. Let me show you what I mean by that. You see this NO3 here on the left side, and you see this NO3 here on the right side? They are identical, right? They're the same thing in a chemical equation. So what that means is that they can be crossed out. Are there anything else that you see that can also be crossed out? Yeah, I see Na+. Na+ can be crossed out. Okay? So these guys that we just crossed out right here, we have a name for them. They're called spectator ions. Okay? They take part in the chemical reaction, but they're not really part of the product if you think about it. Okay, with that, you can rewrite the chemical reaction, and which we call net ionic equation. This is the one that actually shows exactly what's happening and what's really involved, which is Ag+. So what this is that after you scratch out all these spectator ions, you're really just rewriting the equation that are not scratched out. Okay? There we go. AgCl. Don't forget the S. Okay, so here it is. That's the net ionic equation. All right. I do have, some pages in the course pack that I want you to, practice with. So hopefully you guys get all the practices that you need, because the only way to get good at this is really to know how to do this. Now, let me just give you a little rundown in terms of what happens in double displacement reaction. You know how sometimes when you have a double displacement reaction and you say, hey, there's no reaction. What really happened here? Okay, what contributes to no reaction? So let me give you an example. Actually, let me do another net ionic equation first. Okay, that has I guess that has more than one in terms of coefficient involved. Okay? So that way you see a different scenario. So let me do one more of these first. Okay, so the idea here is, let me come up with one. Oh yeah, let's do this one. Let's say NiBr2 plus K2CO3. Okay, there will be some sort of coefficient here. You can bet on that one. All right, to do a double displacement reaction, you will of course do this. This will become nickel 2 carbonate. Okay, plus potassium bromide. And by balancing it, you're going to have 2 potassium bromide. By looking at the solubility table, you'll note that, hey, nickel 2 carbonate is, is a precipitate. What that means is that everything else are dissolvable in water. Okay? How am I going to put this in a net ionic equation? Because this one is a little different. It's very simple. Okay? So let's do the total ionic equation first. Okay? So just like what we did earlier, we're going to break apart nickel 2 bromide. What happened when nickel 2 bromide meets water? Well, nickel 2 bromide will separate into nickel 2 plus and bromine minus. Now. If you look at the ratio here, for every nickel, it is bonded to 2 bromine. So you can't just say this will break up into this, because the numbers will not match. It has to be balanced, right? It has to be balanced, because NiBr2, Okay, if they were to break up, it will give you Ni plus Br minus. But if you can see, Br is not balanced. You have to put a 2 there, stating the fact that when NiBr2 breaks apart, you get 1 Ni and you get 2 Br, as in Ni plus and Br minus. There's a difference between, an ion and this neutral state. Big difference. So make sure you put a 2 there, okay? Plus, well, this will break apart, and you're going to get K plus and CO3 minus. 2 minus, sorry. CO3 2 minus. There's no such thing as 1 minus CO3. Well, is that balanced? No. There's 2K. Right? It's in the game. 2K. So don't forget about that. Or else when you guys are, making the net ionic equation, you'll notice, hey, it doesn't all scratch out, cancel out, or whatever. All right. Here's a reaction arrow. Ni will find CO3 to hook up with, so you don't break apart the precipitate, okay, because they are inseparable. Plus, all right, if you look at this is not 1 kBr, this is 2 kBr. So you have to take into that account that there's going to be 2K and 2 Br. All right? You should really put in those AQ. Now, let's take a look at the, this is your total ionic equation, actually. This is your total ionic equation. Now let's take a look at who are the spectator ions. I can see, very clearly that 2Br will cancel with 2Br. Okay? Now, no. You know what happens? If you only, let's say, okay, let's get rid of this. Let's say you have this, okay, which is not true, by the way. Let's say you have only 1 Br, okay? What happens if you have that situation? It will be just Br and the 2. You get what I mean? Okay? So, but of course, this is not the situation. The situation is that you have 2 bromine here and 2 bromine ions here, and they will both cross out. Okay? But let's just in case if that wasn't a 2, but it's a 1, you would just cross out this Br, but you would just cross out one of the Br. But that's not the case. All right, what else can be scratched out? Oh, yeah, those 2K sports. Yeah, there you go, 2Ks and 2Ks. See you later. Okay, so what are these guys called? That's right, they're called spectator ions. And now we are ready to write our net ionic equation. And the net ionic equation will be Ni2 plus reacted with CO3 2 minus to give you NiCO3 as a precipitate. Okay, so that's what you do when the coefficient, when it has coefficient. So not everything is like 1 to 1 to 1 to 1. And that would be a perfect scenario if everything was like that and life wasn't it. But life is much more difficult, and sometimes there are curveballs. All right, before we finish up, okay, let me just show you exactly what really happens in a reaction that we say has no product. Okay, and I think you guys just say no reaction, but what's really no reaction? So let me just give you this as a side thing. Okay, so I have a reaction right here: copper 1 nitrate plus potassium iodide. Okay. I guess if you were to do the double displacement as is, you will have copper 1 iodide plus potassium nitrate. If you check your solubility table, you'll notice none of these forms of precipitate. Okay, none of those. CuI is soluble. Oh yeah. Potassium nitrate is also soluble. Oh yeah. So what's really happening? Okay, why do we say this is no reaction? Why do we say that? Well, let's do exactly what we did before. Okay, let's drop CuNO3. Okay, no, you know what? Let's do a big beaker. Okay, let's just drop everything in there. Okay, let's drop everything in there. It's really, you can actually do that. It's just that it's not that fun. Let's drop CuNO3 in here. So what happened when you drop CuNO3 in water? Well, you get Cu plus, and you'll get NO3 minus. Right? Well, let's do the same thing. Let's drop Ki in here. So what happened when you drop that in there? You get K plus and I minus. Oh, look at Cu. He's looking around and saying, I just broke up with you. Obviously, I don't want to get back with you. I can't hook up with you. You're also a positive ion. We don't do that. Hi, I. How are you doing? Oh, we don't form a precipitate? I guess we're not hooking up. Nice to see ya, though, I. Nice to see ya. Same with K. K says, oh, I just broke up with you. See you later. Okay, no love in the air. Oh, how are you, nitrate? How are you? You want to make potassium nitrate? Yeah, we can make potassium nitrate, but we'll break up right away. Because we too ain't soluble. Sorry. I mean, we too are soluble. As long as we're in this pool of water, we will all stay separated. There will be no KNO3. Okay? As long as water is here, we're not going to hook up. We're going to stay separated. As long as water is here, we're not going to hook up. We will stay separated. We were hooked up, but we are separated. Same with them. We were hooked up, but we're separated. The water right here has caused everybody to be ion. And because we don't form precipitate, we're all just going to do our own thing. We're all going to go our own separate ways. And don't bother me. Unless somehow you evaporated all the water off. Then we'll talk. Okay? Hopefully you guys sort of have a better graphical view in what double displacement reaction is all about. Make sure you know how to answer those questions. Okay? In class work today, I have some pages in the course pack that I want you to do. Make sure you do them. They're about writing net ionic equations. All right. So tomorrow, or the next class, we'll talk about, we'll do some math. We'll be calculating concentrations of chemicals. All right? Okay. Bye, guys.